All right. Hello, everyone. Welcome to my presentation for the Asian Scholars Network International Conference, CLISI, Kuala Lumpur International Science, Education, and Engineering 2021. Okay, so let me introduce myself first. I'm Jimmy Dozeno, electrical engineer from Badak LNG Technical Department, Indonesia. So for this technical paper, I will be discussing the optimum maintenance strategy for aging industrial uninterruptible power system in the plane that I'm working for, Badak LNG plane. All right, so for today's presentation, it will be divided into four parts. First, I will talk about the introduction on why we did this study. And second, we will be discussing the reliability modeling for the UPS. And in the third part, we will be discussing the developing maintenance strategy. And in the final part, we will talk about the conclusion and recommendation from this study. Okay, so what is actually the uninterruptible power system? So we know that power could be supplied from the distribution line and also from the UPS. So power from distribution line could be very susceptible to several issues like voltage sag, voltage swell, or even like transient voltage surge. Okay, to get a great power quality, we usually use the UPS. So UPS basically is a power electronics equipment that in very basic consists of rectifier to convert AC into DC. It has battery to supply for backup power. It has inverter, static switch. So the output volt from the UPS is controlled and maintained at its very best form. All right. So why we use UPS in the plane, especially in LNG plane? Because many critical equipment could only operate in controlled voltage. I mean, in voltage that within specified nominal value. So when you have a over voltage situation or even under voltage situation, your equipment could be damaged or even it could fail out and cause the plant to shut down and in a very downtime state. Okay, so what is the reason we did this study? First, the manufacturer of the UPS informed Badak LNG plane that the design lifetime for UPS is 15 to 20 years. Meanwhile, in the plane right now, most of the existing UPS population are over 20 years. Since we know now that UPS are immensely critical for plane operation, then we should develop a maintenance strategy. So that's why we did this study with several objectives. First, we want to model the UPS to its smallest functional component, to its identification for statistical reliability assessment and aging UPS maintenance program. And then we will try to review the failure data from both statistical reliability assessment as well as developing UPS aging mechanism. And we want to also develop maintenance strategy to extend UPS operational lifetime beyond its design lifetime. So this is the framework study that we did. First, we collect data from CMMS, which means a computerized maintenance management system, the ODS from the operation, manual book, electrical reports, and we did some literature review, such as the standard handbook, to prepare what kind of methodology that we need to do this study. And after we did that, we tried to process all the data. We did this simulation and review the result. And at the end, we want to develop maintenance strategy that will mitigate the UPS aging condition. All right, now so we move on to the second part. So for this study, this is the thought of process that we did. First, we develop UPS model, then we review UPS failure data, And from there, we go into two directions. First, we evaluate from statistical reliability metrics standpoint, and then we also evaluate from physics of failure approach. So now we develop UPS model. So this is the type of UPS topology that used in Badak LNG plant. So we have the parallel redundant topology where the UPS consists of two main UPS unit, let's say UPS module A and UPS module B, and it also has the bypass unit. So we model this UPS into what we call as RBD, which short for reliability block diagram. For example, this one, the UPS as a system consists of three subsystem components, UPS A, B, and also the bypass unit. However, the actual UPS is way more complex than the previous that I show you, because UPS consists of main power circuit, it has control circuit, it has sensing devices, it has metering components. So from all of these small components, we turn them into a smaller RBD, smaller block diagram. And from all of these components, we classify them based on its characteristic. So finally, we group all of those smaller components into five main components, which are the semiconductor switches. It has PCBA electronics. It has passive power components, protection devices, and battery bank. So finally, we get the final model for UPS parallel redundant that we use in the plans. It consists of UPS A, B, and C, the bypass, and also each of subsystem consists of several group of components. All right, now so we review UPS failure data. So this is the failure data that we have for our UPS. In the past 25 years, there were 4 times where UPS failed. And we found out that the cause of failure was the battery condition that was bad during incoming power outage. So when we have outage in the incoming power, and then the UPS tried to switch to the battery. However, the battery was in a very bad condition, so UPS finally tripped out and the critical load was disrupted. All right, so that was problem on UPS as a system. However, for UPS component, we have several issues where the component suffers some problems. However, it didn't cause the UPS to fail. As you can see here, we have almost 50% problem related to cooling fan and batteries, capacitors. However, several components, especially critical components, up until now never suffer any failure. So we have like critical controller cards, semiconductor switches, transformer, inductors in the UPS that never suffer any failure. Based on this reason, both of these main groups of components will define how long UPS will last. So now we review UPS performance from statistical reliability. Now, as you can see here, this is the step that we use. First, we need to input all of the failure data for each components. We select what kind of distribution model that we want to use. And then we select the estimation method to get the parameter for each component. So after we model them to the reliability simulation software, finally we get the result for 5 years project time, the RBD simulation result in 100% availability. Now, what about the physics of failure approach? So physics of failure approach means that we want to identify what kind of stresses that will be experienced by each component, which will cause all of the UPS component to suffer failure eventually in the future. So we did collect all of the stressors that are present on UPS, such as the thermal stress, humidity, mechanical stress, chemical stress, contaminants, and so on and so forth. And finally, we developed the identification for each cause that will add to the aging mechanism for each stressors. So based on that, we improve the maintenance program in the future. So we have three maintenance program. First is the overhaul program, and second is improvement on UPS unit maintenance, and the third is the improvement for battery unit. So for the overhaul program is related to replacement that should be replaced periodically, that we get all of the data from the UPS component failure. So here, as you can see, for AC and DC capacitor, the overhaul program will be scheduled for every 8 years, for DC current transformer every 8 years, for fan, and also for UPS load test, it will be scheduled every 5 years. Now, what about the maintenance improvement for UPS? It consists of several type of maintenance aging program here. As you can see, there are several issues such like end-of-life accelerated aging. The mitigation is to measure all of the components data, and we add them into the preventive maintenance task. For semiconductor switches, we will train the ripple factor and harmonics content. For the PBAC, the printed board assembly circuit boards, we will try to improve the handling for this using some special gloves to avoid ESD, electrostatic discharge. And for other components, we will try to see whether we will replace them periodically or no. So from there, we develop several tasks. For example, for capacitor, we will measure the capacity in farad, and also we measure the ESR. ESR is short for equivalent series resistance. And also for transformer, we did some insulation resistance tests. For electronic cards, we did the detailed board inspection. So board, as we already discussed before, is one of the most critical components that we need to evaluate, and also we need to always observe to ensure that UPS will sustain its operation for the upcoming future. There are several component aging conditions that we could observe on UPS board. For example, degradation, delamination, functionality deterioration, board cracking. So we did some visual inspection on all of this board, and we try to find whether this kind of mechanism has started on all of UPS critical controller cards. And for the battery, we also developed several improvements for battery maintenance. So here we did the annual load test. Usually for load test is scheduled every 4 years. Since now we know that battery is very critical for UPS operation, we did the annual load test every year. And for the impedance battery, we train them every 3 months. So by doing this, we hope that we could detect battery condition earlier before they suffer any failure during UPS outage power. So the conclusion for this study first, we already modeled UPS into into its diagram block using RBD method, and we also did the simulation using reliability software, and we found for 5 years mission operation, UPS will sustain its maximum availability. And also to extend UPS operation, we improved the maintenance program. Consists of UPS overhaul, additional UPS maintenance, additional battery maintenance, and the last one is recommendation to get a much better prediction for UPS remaining lifetime. We should do some kind of accelerated aging test to get a much more exact number how long will UPS last. So that's the end of our presentation today. Thank you very much for listening. See you next time.